I don't have to shout now. Welcome, everybody. My name's Richard Moorhead. I'm a professor in the Faculty of Laws. I'm just here to chair today's lecture. We're delighted to welcome Professor Brian Butterworth. I've done a few of these this year. This is definitely the best title. Brian, I'll just hand over to you.
Right, well, can fish count? Thank you for that comment on the title. I'm going to explain in some detail the arguments I'm going to be making, just so that you don't think there's something fishy going on. Oh, great, okay. Why you might think this is a silly question, part one. Well, here's a picture of the brains of humans and fish. Fish have very small brains. Humans have very large brains. In fact, humans have at their disposal, for counting, a brain with 1,000 million neurons, whereas fish have round about 1 million neurons. And I'm just going to be talking about very small fish who probably have rather fewer neurons than that. Why you might think it's a silly question, part two. Well, you might think that only humans can deal with abstract concepts. And numbers really are abstract concepts. They're abstract properties of sets, which are themselves abstract. You might also think that counting is essentially a human construct invented about 10,000 years ago when people started trading at a distance around the Mediterranean and elsewhere. An argument that's been advanced by many people recently is that counting depends on language. So it's been argued that a vocabulary of counting words is necessary for a person to possess the concepts of exactly 4, exactly 5, and so on. That is, you can't have a concept of exactly 5 without having a word for it. And if you don't have a word for it, then only approximate numerical values are possible. And many, as I say, many people have advanced this argument, and Chomsky perhaps was the first to argue for the dependence of numerical capacities on language. In this quote here, the human number faculty is essentially an abstraction from human language. So, just to show that there's really nothing up my sleeve, I'm going to define what I mean by counting. If requires reciting counting words, then of course organisms without counting words can't count. However, if it means enumerating exactly the objects in a set, then maybe they can. But how can we test the ability to count when the organism has no counting words? Well, there are two ways. Can the organism identify the numerosity of a set, a particular numerosity, let's say 5ness? Can the organism discriminate the numerosities of 2 or more sets, say this set is more than that set, or this set has 5 and that set doesn't? Now, in order to do the appropriate controls, we have to make sure that the organism is attending to what I call the numerosity of the set, or cardinality, how many objects there are in it, when the membership of the set may differ. So you might have 5 apples and 5 bananas, and you want to know if these two sets have the same numerosity. Of course, the members of the set needn't be concrete objects. They could be, for example, sounds, like the number of sounds I'm going to make now. In fact, the objects can be abstract objects, as long as they're distinguishable. For example, it could be 5 wishes. So, is it necessary to have counting words to count? Let's consider first humans whose language contains no counting words. Are there any, you might ask? Counting has been important for trade since the agricultural revolution 10, 12,000 years ago, so most languages do have counting words. However, there are some which don't, and particularly those that with no history of trade at a distance. In fact, most Australian languages and some Amazonian languages don't have counting words. So how can we test whether people, humans, who don't have counting words can actually enumerate a set? Well, one method is called match to sample. So here's a sample of objects in a set, which I've defined here by a rectangle. And the task of the organism is to select one of two possible sets which has the same number of objects as the sample. So that's identification by selection. You could also have identification by construction. I'm going to give concrete examples of these in a minute. So what you have to do is create a set with the same number of objects as the sample. And you have to make sure that what people are attending to is the number of objects in the set rather than the properties of those objects. So you have to select the match here. Indeed, the objects may not be distributed at one time. Like I've just shown you, they could be distributed in time, and you have to be able to match objects distributed in time with a set that's distributed in space. So here's an example. And you have to match it to one of those two. Okay? Now another way of doing it is seeing if people can discriminate two sets with different numerosities. I'm going to show that there's some data here which we can use in order to test this, and it's called the distance or ratio effect. So if you take a display like this and you have to say, are there more squares on the left or the right? Oh, you didn't mention there was going to be a test, Joy. There will be a test later. Okay, right. So you have to say whether they're more on the left or the right, and there's a well-known effect here called the distance effect, or sometimes the ratio effect. And along the bottom here you can see the distance, the difference between the two arrays. And if the arrays are very similar, it's more difficult, it takes you longer. If they're very different, it's quick, and that's called the distance effect. You can even do it for quite large sets, like here, as they're more blue or more yellow. So in rectangle A, it's very easy, there are more yellow. In rectangle B, it's a bit more difficult because they have a similar number of blue and yellow dots. And this is data from quite 14-year-olds, and it shows that as the ratio gets bigger, so let's say there are twice as many blue dots as yellow dots, then it's very easy, you get almost all correct. But where if there's only 1.25 as many blues as yellows, then it's a bit more difficult. But of course, these are experiments done with people who actually have counting words. But do we really need counting words to count in humans? So here's some data that we've been collecting from Australia in two sites with two different languages. A site in the central desert called Willara, where they speak a language called Walbiri, which has a word for one, a word for two, a word for few, and a word for many, and it has no traditional counting practices. In Ngurungu, where they speak a language called Anandiliagwa, which actually is unrelated to Walbiri, they also have a similar vocabulary of number words, which I'm happy to go into. So let me just tell you a bit about these two sites. This is picture's taken at Willara. It's in the desert, and we're testing kids who are on the whole monolingual in Walbury. And this is our researcher, Delith, and she's holding in her hand a witchetty grub. So I suppose it's a case of, I'm a researcher, get me out of here, because they eat it, and so she's going to have to. This is our other site on Groot Island, off the north coast of Australia, where a lot of fish around. In fact, since we first went there, there's now a resort where you can go and fish for barramundi. Apparently a very nice resort. I haven't been there. I just want to show a picture of a salty. It's a large crocodile, which occasionally takes humans. So I just want you to realize that the danger that we sometimes encounter in collecting our data. So I'm going to show you 3 tasks. Identifying numerosities in a memory for counters task, which is essentially identification by construction. Identifying numerosities across modalities, cross-modal matching task, again using identification by construction. And finally a task of adding numerosities. So this is the basic setup. This is our other researcher, Fiona Reynolds. And this is our lab, very high-tech lab. So we have 2 bits of brown paper, Fiona on the left, our subject in the middle, and a translator on the right. We need to be able to present the materials by a native speaker. And although Fiona actually does speak Samana de Liagua, she isn't a native speaker. So she is showing a number of red counters on her bit of paper, and she is going to now cover them up and is asking the subject to put as many counters on her bit of paper as Fiona had on her bit of paper. Now, you might think, well, you can do visual pattern matching here. And in fact, children in both Willara and Angurugu do actually use pattern matching as a strategy for solving this task. However, they can't do it for the next task, which is cross-modal matching, where Fiona bangs out some bangs, and the subject has to put out as many red counters as there are bangs. And there she is doing it. Addition, you'll see exactly the same pictures because the setup's the same. Fiona will put out some red counters on her bit of paper. She'll cover them up, and then she will add, in full view of the subject, some additional counters that go under the blue bit of cloth. And so what the subject has to do is represent the number of objects that are now under the cloth. So there is the subject doing it. And it turns out that these children in Willara and Angurugu do this just as well as kids in Melbourne. So the green spots are English kids, the red spots are Walbury-speaking kids, and the blue spots are Anadiliagua-speaking kids, and the larger the dot, the more kids are making that response. And as you can see, there's no difference between the 3 groups. This is true also for cross-modal matching and also for addition. As I said, we also assess the kinds of strategies that kids used, and the kids in Melbourne never used pattern matching. They presumably counted in their head, but the young children in Willara and Angurugu used a pattern matching method. So they would visualize the pattern that Fiona or Dennis had covered up, and then they would reproduce that, at least very often. The older kids did that less. Okay, this is just to show that humans who don't have counting words can do this sort of task, which requires exact numerosities as well as kids who are brought up counting. Now, what about wordless creatures? Because those kids, of course, had language. What about can wordless creatures identify numerosities? Well, the first demonstration of this was by Otto Koehler, who was a German ethologist. And he demonstrated this in a series of very beautiful experiments with corvids, jackdaws, ravens, and crows. And so this is the basic pattern. Here you can see this large area is the sample, and if the bird can pick out the right number on that smaller area there, then it will get a reward. If it picks the wrong one, it won't get a reward. And Koehler used a lot of different variations of this, but he always made sure that the potential match had a different pattern to the sample. The same paradigm was used by Andreas Nieder, another German scientist, but this time with monkeys. So what he did is he would show the monkey a sample, then there'd be a delay of a second, and then the monkey had to choose one of two potential matches. Even if the monkey got it wrong, there would be a match, so the monkey is learning, but also the monkey who does badly is as well rewarded as the monkey who does well ultimately. Now, one of the interesting things that Nieder did when the monkey was carrying out this task was he was recording from the brains of these monkeys to see which area of the brain seemed to be responding when the monkey is doing this task. In particular, he was interested in the delay period when, if you like, the monkey was thinking about the number of objects in the sample. And what he found was that there was a very clear effect, that monkeys responded in the intraparietal sulcus, an area I will come back to, and that there were individual neurons that were roughly tuned to particular numerosities. So there might be a neuron that was tuned to fourness, and if four objects were presented, again, this neuron would fire a lot. If 3 was presented, the neuron would fire less. If 2 was presented, even less. If 1 was presented, even less. So there were neurons in the intraparietal sulcus that seemed to be tuned to particular numerosities. Just to ensure that it was numerosities that these neurons were responding to, Nieder and his colleagues carried out 2 important controls. First of all, as I said, the potential match never looked like the sample, but he also wanted to make sure that it wasn't just quantity that these neurons were responding to. So there was a very similar paradigm here, where the monkey would see a line and then had to select a potential match of a line with the same length. And this is the just reorganized the numerosity test and the length test. And what he found is that although there were some neurons in the intraparietal sulcus that responded to both numerosity and length, there were some that responded selectively to numerosity and some that responded selectively to length. And so it wasn't just quantity that the monkey was responding to, or the monkey's brain was responding to, it was actually numerosity. And a further very clever experiment, rather like the demonstration I showed you, having identified, let's say, a neuron that responded to fourness, Nieder and his colleagues would give 4 blobs in sequence, blob, 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 blob. And then the monkey had to select from a display like this. In fact, there were 3 in this particular example. So it was having to match a set distributed in space, in time, with one distributed in space. And what he found, for example, for a neuron that responded selectively to fourness, is that it responded more to 4 than to 3 than to 2 or to 1. And the particular area in the brain he located was here in what's called the fundus of the interparietal sulcus, the bottom of this groove in the brain. And it turns out this is exactly homologous to an area that we found when we were able to distinguish between numerosity from continuous quantity in humans, the fundus of the interparietal sulcus. Monkeys can also do cross-modal matching for number. So here, this is an experiment by a lab at Duke University. The monkey hears, let's say, 3 voices, 3 monkey voices. And if the monkey hears 3 monkey voices, it will look more at a display of 3 monkeys making a noise than 2 monkeys making a noise, though, of course, he can't hear them. He can't hear these particular monkeys synchronized. What he's hearing is 3 monkeys jabbering away, and he will attend selectively to a display of 3 monkeys. So that's monkeys. Now what about chimpanzees? Here I'm going to show you a bit of film, if it works. This is a very well-trained monkey. I'm sorry about picture quality. I'm the world's worst cameraman, so I apologize for this. What this monkey has been trained to recognize the digits and to associate the digits with numbers of dots. So I'll just show you this chimpanzee, who's about 20 years old when I saw her. Oops, let's do this. And that's 0, okay. So this is just some data from a paper that Matsuzawa, who's the lab leader, and his colleague Tomonaga presented. This is, just look at the response times for this chimpanzee versus humans. When you get to quite large numbers, the chimpanzee is quite a lot faster than the humans. They're not really quite as accurate, at least for in this task. Now, as I said, chimpanzee I knows what the numbers mean in terms of sets, but also knows the order of numbers. So here's an example. Oh, sorry. So what the chimpanzee has to do here, what you should try and do as well, is touch each of the digits in ascending numerical order. Okay. Now, actually, her son, Ayumu, was even... oh, let me just show you this one that you can't do, but this chimpanzee. So what happens here is that the numbers are covered up 210 milliseconds after their first check. Then he has to touch the mouse. Okay, so... now, I'm going to skip check arithmetic and go straight on to fish, because I'm taking rather longer than I'd thought of this. Right, can fish count? Get to the heart of it. So here are some fish swimming around.
Where we have the lights on, 14 hours of light and 10 hours of dark year-round.
Okay, so we're testing little fish, and this is how we do it. These little fish like to swim in shoals, and it's adaptive for them to swim in larger shoals. So can they select the larger... Oh, actually, no, I don't have to finish at 1:45, do I? I have to finish at 5:45. I thought I was wrong. Okay, let's go back. Sorry about that. Okay, let's show you some chick arithmetic. So the question here is, can one-day-old chicks do arithmetic? Hands up who think one-year-old chicks can do arithmetic. Well, there are a few of you. Okay, so this is, let me show you the paradigm. Okay, so this is a one-day-old chick, and she's being shown some Kinder eggs going behind the screen, okay? So this is sequential, okay? So she sort of has to count. Now, chicks, as you may know, imprint. That is, they will follow the first thing that they see once they're hatched. And if they can see a few things here and not so many there, they'll follow the more things, because they're more likely to be nest mates. So they prefer larger sets. Okay, so now it's seeing one Kinder egg going from behind that screen to behind that screen. Okay, so there's been an addition and there's been a subtraction. Now, is the chick going to be fooled by the fact that something's just gone over to the left? The chick is thinking. There she is. Right. Okay. Right. Now, that's very simple arithmetic. Now I'll show you the experiment that was, I think, particularly impressive. So here's a chick, and it sees objects, one object going there and then 4 objects going there. So it can think about it. If it's thinking 4 objects here, 1 object there. Then 2 objects go from behind the left-hand screen to the right-hand screen, so that there are now 2 here and 3 there. So in order to know where there are more Kinder eggs, the chick has to do an addition and then a subtraction. And in fact, the chick does this quite well. Or else it wouldn't have been published in the Proceedings of the Royal Society. Okay, discriminating numerosities. I'll just show you one example of this. This is a classic experiment done by Liz Brannan and Herb Terrace, and this is with two monkeys, and what they had to do is they had to select the larger of 2 displays. And these are examples of the displays, and they went up to 9 items, but you can see that they're very different from each other, so you might have 4 of these and 9 of those. And so the monkey has to select the 9. And what they found was that both monkeys not only could do this way above chance, but they showed a distance effect. So when the difference between the 2 displays was 1, they were only about 80% right, but when the difference was 8, they were almost 100% right. So monkeys can do this, certainly. Okay. So now we get on to fish. Okay, finally get on to fish. Okay, so we've seen that. So this is our standard procedure. We have a subject fish in the middle of this transparent tank, and in the 2 side tanks, the subject fish can see some number of conspecifics on the right and on the left. And what the fish has to do is to select well, what the fish will do, we don't have to train the fish to do this. The fish will just spontaneously select the side with more conspecifics in. Now, I haven't told you this, but I'm going to come back to it in a few minutes. We have two numerical systems, two pre-verbal numerical systems, one for small numbers and one for large numbers. So do guppies, these are our subject fish, have two numerical systems, just like humans. There is some human data which we collected because this experiment was done in Italy. We used Italian students to see if they had two numerical systems. They did, though we didn't put them in tanks and ask them to swim around. But one of the things about the small number system is you don't get a ratio effect. In the large number system, you do get a ratio effect. And here you can see that guppies, both young and experienced guppies, show no ratio effect in the small numbers, but do show a ratio effect in larger numbers. So as the ratio, the difference between the two sides of the tank is smaller, then they're less accurate. But my colleagues also did a numerical identification experiment with these guppies with abstract stimuli. Okay, so the guppy is put into the middle of this tank, and it's rewarded if it goes to 3, and not rewarded if it goes to 2. And they varied the way in which the 2 and 3 were displayed. So here's what the experiment looks like. Here you've got a fish in a tank in the middle of a tank, swimming around, and when it gets to 3, it'll be rewarded, and so it should have learned. And then, after learning, it should go into the right display. It goes through the right display, and it comes out and can join its friends. Now this is simultaneous presentation, but my Italian colleagues devised a very clever way of getting sequential presentation of fish to the subject fish. So here what you do is you put each of the stimulus fish in separate little compartments so that the subject fish can only see one at a time. And even with that manipulation, the subject fish does rather well at discriminating numerosities. Now, one of the things that we found with humans is that if you have 2 humans making a numerical decision, they do it better than 1. Now, the setup is this. You have 2 people in a room, each looking at their own computer screen, doing the blue and yellow number discrimination task. They do it separately, and if they disagree, that is, if one presses blue and the other presses yellow, the stimuli disappear, and then they discuss it, and they come to a joint decision. So they don't have a chance to review the stimulus itself, they just have to discuss it, and then they come to a joint decision. And the joint decision is better than the individual decisions of either of the 2 subjects. And we had a theory about this called weighted confidence sharing, which is a kind of a fancy way of explaining what's going on in the head. Anyway, we thought, wouldn't it be fun to try this with fish? Now, although fish go, it's not clear that they talk to each other. So what we did is we put 2 fish in the stimulus area, but they had to make a discrimination. And what we found was that 2 fish make a discrimination better than 1 fish by itself. But what we also discovered, which may be like weighted confidence sharing, is that the more confident fish would lead the other fish to the side with the more stimulus fish. And we called this meritocratic leadership among guppies. So the less good fish would follow the better fish. This was true also when we used abstract stimuli, but kind of, I don't know if you can quite see this, blobs on a screen. And again, if you put two fish in there, they do better than the average of each fish, but they do as well as the better fish of the two. So, how do organisms count without words, and what kind of mechanism could there be? Actually, it's very simple. Here's a possible counting mechanism, and it goes back to an idea of John Locke's. I'm not sure if the people who invented this actually knew about John Locke's idea, but I did, so I'm going to give it to you. So, in an essay concerning human understanding, Locke said, the simplest idea is one. This can be repeated, and by adding repetitions together, we get complex ideas of larger numbers. Thus, by adding one to one, we have the complex idea of a couple, etc. We should give each complex idea a name or a sign whereby to know it from those before and after. And this idea, with I think no reference to Locke, was revived by three important researchers, actually in baby mathematics, which is another area I'm not going to talk about today. The concept of one is innate. There's an adding mechanism which is also innate. And how might that work? They use an idea called the accumulator, which comes from some rat counting experiments, which I don't have time to describe. But the idea here is that every time the rat experiences a relevant stimulus, it, if you like, adds one cup to a beaker or an accumulator. And at the end of the process, the contents of the beaker are added into a memory beaker. And so if there are two sets of things, it can compare, if you like, the height of the liquid in the two beakers. Now you might think, well, of course we don't have beakers in our heads or little cups. But the critical thing about having one cup per item is that you normalize the objects. So all objects are represented in the same way by the metaphorical cup. So in the Meck Church idea is there's a kind of a pacemaker in the head, and there's a gate that opens for a fixed amount of time for each object that's experienced, and then an accumulator records how many objects there are. And Hahn and Changeux, 10 years later, had a system whereby objects that are distributed in space, which could be very different, are also normalized and then are added to an accumulator. Now, finally, why is this important? Well, it's important because we're interested in which cognitive capacities we inherit, and therefore which we may fail to inherit. Now, 3 to 5% of humans are very bad at identifying and discriminating the numerosity of sets, believe it or not. And they are called developmental dyscalculics. And it turns out that this capacity is essential for learning arithmetic. So you can give humans a test like this, which is larger, and this is a study by my student Manuela Piazza, and what she found is that dyscalculics are much worse at this. This is how good you are, you get better as you get older, and they're about 5 years behind their, right, okay. But we can also do an identity test. Now, this is your test, then we finish, okay? How many dots are there? Shout out the answer as quickly as possible. I'm going to whiz through this.
1, 4, 6, 9.
Okay, there's a relationship between how many dots and how long it takes you, and also how likely you are to make an error. And what we found is that performance on this task in kindergarten predicts how well a child is going to learn arithmetic up until at least the age 11. And therefore, knowing that this particular capacity is inherited is actually very important from an educational and indeed an individual human point of view. Thank you very much. The end.
Thank you ever so much. I think we don't have time for questions, but we did get the film with the chick in it, which I think was definitely worth compensation. And so, Brian, thank you. That was really fascinating, and not only the best title, probably the worst joke, but the best videos. So we're very grateful indeed. Thank you.